Hello and welcome to today's lecture. So, in the last class we were discussing how to go about quantifying or characterizing the properties of ECM networks. Okay. And in that regard we had introduced the terms of rheology, okay, which is the field of that studies how materials deform when subjected to force. We had also discussed what are different types of deformation we can impose on a material. So, these include tension, compression, shear and bending. Okay. So, tension compression is very clear, bending is where instead of something straight you exert forces, so that the final configuration is something like this. Okay. And shear we had discussed in great detail, where if you have a block you exert tangential forces on the top surface, as a consequence of which the block deforms to a shape like this. Okay. So, and this delta x, so delta x by L, this is my length L and this is delta x, this is what is given by your shear. Okay. Now, we also said that what is the difference between behavior of a solid, a perfect solid versus a perfect liquid. Okay. And the main difference is, for a solid, okay, you write down this expression where shear stress is given by G times gamma. G is called the shear modulus. Okay. And G, so for incompressible materials we had shown that Young's modulus of elasticity. So, this is shear, you can write sigma is equal to E epsilon for normal stresses. So, E is given by 3 times G for incompressible materials. So, tau is equal to G gamma for solids, and for liquids you have Newton's law of viscosity, which is tau is equal to mu into du dy. Okay. And what is du dy? So, du dy is nothing but ddt of dx by dy. Okay. So, dx by dy is nothing but the definition of shear, which is gamma. So, this is nothing but ddt of gamma, this is equal to gamma dot. Okay. So, this equation is same as writing tau is equal to mu gamma dot. So, the main difference is, in a solid tau is proportional to shear, for a liquid tau is proportional to shear rate. The constant of proportionality here is the shear modulus, the constant of proportionality here mu is viscosity, right. So, for tau is equal to mu gamma dot, okay, mu is viscosity, okay, and we showed. So, units of mu is Pascal second in MKS units, and in CGS units we call it as poise or simple P, we write it as simple P. Okay. So, mu of water is 1 centipoise at room temperature. It is also important to say that mu has a dependency on the temperature. Okay. Now, for materials where mu is constant independent of shear rate, this is called a Newtonian fluid. Mu is constant and does not change with gamma dot. Okay. So, I had shown this slide in last class saying that ECM networks are viscoelastic. So, as opposed to, let us say this is my stress strain curve. For linear elastic materials my stress strain is linear. Okay. For nonlinear elastic materials, so this is nonlinear, that is E is not constant. Okay. And here E is constant. Why? Because the slope of the line is E. Okay. For viscoelastic materials like ECM networks. So, this is a simple example of how the stress strain curve would look if you make a collagen gel and put it in a uniaxial tester which kind of keeps on pulling it repeatedly. So, what you see is, so the repetition is corresponds to the cycle number, and what you see is the path by which it follows in the stress strain curve when you exert, when you stretch it and when you relax it is different, and also the average slopes of these lines keeps on increasing with the increasing passage of cycle number, suggesting that there are some dynamic rearrangements which happen. Okay. So, this is what we want to focus now as to what are those attributes of a ECM network which dictates its functional properties. Okay. And you would remember this picture I drew from last class saying that the scaffold that you create in terms of its organization, here I have drawn one as random and one as aligned. These have robust effects on how cells process these cues. So, for example, on a random matrix, cells will tend to migrate in a random fashion without any persistent motion, while on an aligned matrix like that, the cells will not only stretch itself along the alignment direction of these fibers, but also tend to migrate along these aligned fibers, taking them as a directional cue. Okay. So, how do we characterize the properties of these random versus aligned matrices? And what I suggest is the properties of these collagen scaffolds depends on two things, okay, cross-linking and alignment. Okay. So, alignment is very clear in this, but for the same network. So, imagine I had raised this analogy of cooked chow mein, right. So, when you try to extract one strand of noodles from the entire bunch, so this does not come out so easily, even though there is no chemical glue which is bonding them together. There is relative friction. Okay. So, even a random network will exhibit some resistance, so which means it has some bulk stiffness. Okay. But if I, for this random network, let us say I had this random network, in one case if this network is just that these fibers are put together and I exert force on this fiber. So, I will lead to a configuration where this might slowly come out of this network, leaving the remaining two fibers like this. Okay. So, in this case the properties of the network will change dynamically, versus if you had fixed all these points together. In other words, you had cross-linked the network, then when you exert a force here, this gets transmitted to the entire network. So, the network resists that force as a whole. So, the response that you would observe for such a network is drastically different if it was not cross-linked versus it was cross-linked. Similarly, the case of alignment. So, what would be an equipment with which we might be able to probe these properties? Note that these networks are super soft. So, typically a collagen network might have a stiffness order of 1 kPa. Okay. So, this is super soft. So, you cannot use traditional instrument used in material science like indenters, which can only probe the material properties of stiff materials. So, that brings us to what we call a rheometer. Okay. So, what is a rheometer? This is a picture of a rheometer where you have a sample which is placed between two things. Okay. One portion of which, the bottom portion of which is fixed and the top portion of which is rotated. Okay. So, imagine a mortar and pestle in which the top thing you keep on rotating. So, if you put a sample in between, when you exert this rotation, the sample is essentially being sheared. Okay. So, you can essentially probe its shear properties, shear modulus, and if you knew the Poisson's ratio of the material, you can backtrack what is the Young's modulus of elasticity. Okay. So, several things I wish to say about the rheometer. Okay. So, you have what you can do. So, you can do two things. First is you can change. So, you have this setup where you have your sample. Okay. So, this one you are rotating. So, you have control over the rate at which you are rotating. Okay. But you have also control over how much you can indent, you can push into the sample. Okay. So, this is called, so this is you are imposing a strain, okay, with how much you are pushing the sample, and you are controlling the amplitude of rotation or the frequency of rotation. So, strain amplitude is one thing we are controlling, and we are controlling the frequency. Okay. So, again for a pure solid we have T is equal to G gamma, for a pure fluid we have T is equal to mu gamma dot. Okay. So, in general if I were to apply a oscillatory field, in other words I can write, if I were to write gamma as gamma naught sine of omega t, if you exert an oscillatory strain, then your stress field can be written as sigma 0 sine of omega t plus delta. Okay. So, if you expand this equation, so this sigma is then written as gamma dot into so it has two components, G prime sin omega 2 and G double prime cos omega t. This term G prime is called the storage modulus. So, G prime okay, and G double prime is called the loss modulus. Okay. So, if I were to pictorially depict it, you would have a curve like this. If this is your gamma function, okay, you have a phase shift, this is what delta is. Okay. So, this is gamma and this is sigma, this is time. Okay. So, you have one component, so you have sigma is equal to gamma dot into G prime sin omega t plus G double prime cos omega t. So, you have this component which is in phase with the applied strain field, which means that as soon as you exert the strain, immediately the material deforms. Okay. So, G prime or the storage modulus corresponds to the elastic component. Okay. This corresponds to the elastic component, and it is called the storage modulus because this energy can be retrieved. When you release it, you again go back to the original configuration. The G double prime is the viscous component. Okay. And hence it is called the loss modulus because this is dissipated. Okay. This is dissipated. So, how, as I said that when I make these ECM networks, what can I say about G prime and G double prime? What is known in the literature and has been shown by many groups, that if you make gels of various concentrations, that means that if you vary the concentration, let us say 1 mg per mil, 2 mg per mil, etc. So, your G prime will scale as concentration cubed, okay. X is roughly 3 for collagen gels. Okay. For collagen gels, G prime will scale as concentration cubed, which means that in order to stiffen a matrix, you can increase its concentration. However, since cells directly bind to this material, when you are changing the concentration, you are changing the bulk stiffness, but at the same time you are changing ligand density. So, this is one problem of working with collagen gels. if you want to probe the independent effect of ligand density keeping stiffness constant. That is why people tend to use synthetic substrates where they can control its stiffness and then independently functionalize ECM proteins like collagen onto those substrates. Okay. So, this is one aspect. The other aspect, again coming back to the linear versus non-linear materials. So, what I have shown here is how cells would spread on materials of different stiffnesses if it was a linear material, linear elastic material, case of polyacrylamide hydrogel, or a non-linear material. So, what you see of cell spreading in linear materials is that when you increase the stiffness, cells spread more and more, and beyond a certain threshold there is no change in cell spreading, it saturates. Okay. But if you take a non-linear material, okay, no matter what concentration you start from, okay, whatever is its initial stiffness, you see that cell spreading does not have any dependence on stiffness. So, suggesting again that there are these rearrangements which can happen, which can drive this increase in stiffening. So, this is saying that whatever be the starting stiffness, when you put cells on it which pull on these matrices, the matrices deform and become stiffer in the process. Okay. So, this is called strain stiffening. This is called strain stiffening, and for fibrin, similar to fibrin, collagen gels also have been shown to exhibit this profile. So, if I plot the storage modulus as a function of strain, what you find is at a given concentration, first your storage modulus is constant, and beyond a certain strain, okay, beyond a certain strain, it starts to increase. So, it becomes nonlinear in nature. Okay. So, this phenomena is called strain stiffening. Okay. And then the red line, so you have another variable, because you are for just by the concentration alone, by playing with the concentration alone, you can get more and more stiffening also. Okay. So, that is why the red curve is above, initial again flat, and then it rises. So, you see that there are two independent ways in which you can, in which cells can stiffen collagen gels. Okay. So, first is for a given ligand density, just by exerting forces, the gels become stiffer and stiffer. And the other is that just by playing with the concentration alone, you can generate materials of different stiffnesses. Okay. So, this brings us to the question that what is driving this behavior of strain stiffening. Okay. And what it turns out is, as I was drawing before, when you have increase in strain, then individual fibers tend to along the direction of strain. Okay. So, as opposed to having a network like this, when everything gets aligned, then the fibers, then the effective stiffness increases in that direction. So, anisotropic, the stiffness is anisotropic in nature. In one direction it is very stiff, okay, and it can be experimentally probed by checking the orientation of fibers within a gel. Okay. So, if I take a collagen gel, let us say, okay, where you have fibers in all directions, okay, and I align them actually, okay, I pull this matrix along the long axis. So, if I draw the average orientation as a function of average orientation of fibrils, what I will find is I will find a uniform distribution, a normal distribution, okay. So, which suggests that there is equal propensity to find fibers which are oriented in one direction or the other direction. Okay. But as I align more and more, okay, so as I align more and more, you will see they will generate this kind of geometries eventually where everything is aligned in one direction. Okay. So, your average axis, so your average angle will change, and from here in this particular case you will see that everything will align along 0. Okay. If this is 0, close to 0, you will see everything will align along 0. So, this is what drives stiffening. Okay. However, one of the things about this network is if it was not cross-linked, when you remove the force, when you remove the force, the alignment of these fibers remains in the final configuration. So, from here you do not go back to this configuration. Okay. So, how would you do that? And the way to do that is essentially cross linking. Okay. So, the way to do this is to cross link it. So, when you have two fibers, if they are cross linked at this point, when you tend to force along this direction, they will align, but as soon as you remove the force, they will come back to its original configuration. Okay. So, this suggests that you can, so you can do these experiments in which you can track the angle distribution as a function of pulling and as a function of cross linking. So, you will see that if it was an uncross linked gel that you made, your angle evolves and then stays put at the final configuration. But if you take a network which was cross linked, one you will see that if it was 100% cross linked, first it will even its basal stiffness will be increasing, but the other thing is it will keep on returning to the same position. So, if you do it in an oscillatory way, so let us say what I am doing is I am doing it in a sine Wt fashion. So, my strain is some gamma naught into sine Wt along the x axis. Okay. So, what you will see is the angle distribution will keep on changing like. Okay. So, let us say your angle increases, okay, and when you release, so at this point you relax, the angle will keep on coming to the same position. Again you increase, so this in this stage you stretch, here you relax. Okay. So, your angle will keep coming back to the same configuration after you remove. Okay. So, that is about it for our discussion of collagens and their material properties. I would ask you to read these two papers, one on which and how cells can sense nonlinear stiffness and how they change their properties in response to nonlinear stiffness, and the other one the other paper is about this orientation and effect of cross linking and alignment on these fibers. So, both these papers have been published in PLOS ONE, which is an open access journal, which means that you can download these papers anywhere. You do not need any special access to be able to download these papers. So, in this course I will give you reading assignments in which I will recommend you to read certain papers. So, it is mandatory if you want to follow up of what we are doing in class, then it is mandatory that you read these papers. Even the quiz questions that will be asked in the course will be posed from these particular papers and the content which has been covered in the class. Okay. So, that brings us to a close on our discussion about collagen. We will discuss about one more protein. So, I do not have much time today, I will just introduce this protein is fibronectin. Okay. So, fibronectin is a protein which has dimers of two similar polypeptides which are linked by disulfide bonds. Okay. And fibronectin has that RGD sequence which is critical for cell addition. Okay. So, and that has led to peptides, adenosine peptides of RGD being alone used for sustaining cell spreading or cell addition. Okay. So, fibronectin is known to bind to collagens, proteoglycans and other things. It plays very important role in migration, differentiation, wound healing, and it is secreted by many adherent cells. Okay. So, if I were to draw the structure of fibronectin, okay, so you will have multiple units, okay, like this, and at the end you have these disulfide bonds. Okay. So, these individual domains are referred to as FN1, FN2 and FN3 domains. Okay. So, you know, for any protein which has multiple domains, for its function it folds into one particular structure. So, the question that I am going to ask is how does folding of the protein participate in regulating signaling, and how does forces influence the folding kinetics of this protein and its role in subsequent function. Okay. So, this is just to give you an intro to fibronectin. We will start discussing in detail about fibronectin in next class. Thank you.